Howdy. So what have we learned so far? We've learned the second law of thermodynamics says that for every spontaneous change, there's an increase in the entropy of the universe. And so if we want to know if something is going to occur or not, we just have to know, will that increase the entropy of the universe? Now also please note that in this context, spontaneous does not mean occurs instantaneous. Spontaneous means it occurs without any outside intervention. We've also learned that the best way of thinking about entropy is in terms of S equals K natural log W, where S is entropy, K is Boltzmann's constant, ln is natural log, W is the number of configurations. And so this is the best way of thinking about entropy. Now, when we're talking about configurations, we could be talking about positions of atoms or molecules, relative orientations of molecules, or actually ways of filling energy levels. Now, we can relate these different types of configurations to composition, intermolecular forces, physical state, and temperature. And so in terms of composition, the more atoms per molecule, the more energy states you're going to have, and hence more possible ways of filling those energy states, and so higher entropy. In terms of intermolecular forces, the stronger the intermolecular forces, the fewer number of configurations in terms of positions or orientations, and hence the smaller the entropy. For physical states, for a compound, a gas will always have higher entropy than the corresponding liquid, which always has a higher entropy than the corresponding solid. And in terms of temperature, the higher the temperature, the more energy states are accessible, the higher the entropy. And also we saw that we can think about the universe as composed of two parts, the system and the surroundings. And we define the system as a closed system, meaning the only thing that can transfer between system and surroundings is heat and work. So no matter can go from the system to the surroundings. Now today I thought we'd talk about energy changes when heat is added. And again, delta S universe equals delta S system plus delta S surrounding. And so we saw that if we want to know if something's going to occur, we have to know how it affects the entropy of the universe. And we'll see that the above equations actually help us determine how the entropy of the universe changes. Now, hopefully after watching this video, you should be able to calculate the change in entropy of a system or the universe based on heat transferred, when there's a change in temperature, and when there's not a change in temperature. You should also be able to determine the change in entropy of the universe, remembering that the only way that surroundings entropy is changed is by the transfer of heat or work. And so S equals K natural log W, again, is the best way of thinking about entropy. We call this the statistical entropy. The thermodynamic entropy is delta S is equal to Q over T. Now again, these are actually equivalent. You can do some problems and actually get the same answer using these two equations. But again, for S equals K natural log W, I think that's the best way of thinking about entropy. And often we'll use delta S equals Q over T to actually calculate the change in entropy. And so when you heat something, are you increasing or decreasing the entropy? Well, when you heat something, you're going to access more energy levels, and so more ways of filling those energy levels, and so it can cause the entropy to increase. And so the change in entropy of the system can be determined from the amount of heat transferred to the system when there is no chemical reaction. And so when there is a chemical reaction, typically we do products minus reactants. But when there is no chemical reaction, like in a phase transition, we can just use delta S system equals delta H over T. Now remember, delta H is your change in enthalpy under constant pressure and assuming only expansion work. Delta H equals Q, which is the amount of heat transferred to the system. But again, if there is a chemical reaction, you have to use products minus reactants to calculate delta S system. So this top reaction, delta H over T, is only when there's no chemical reaction, like if you have a phase transition. But if you have a chemical reaction, you have to do delta S equals products minus reactants. Now thinking about how we define the system, the only thing that goes between system and surroundings is heat and work, and typically we ignore the work. And so if delta S system is delta H over T, and again, delta H is positive, heat is transferred from the surroundings to the system, then delta S surroundings would be minus delta H over T. So again, if delta H is positive, heat's going to be going to the system, and the entropy of the system will be increasing. Again, if delta H is positive, then his surroundings is losing heat, and its entropy is decreasing. Now this is a little confusing because if delta S universe is system plus the surroundings, wouldn't that always mean that delta S universe was 0 when there's no chemical reaction, right? So we have the system is delta H over T, surroundings is minus delta H over T, and the universe is delta S system plus delta S surroundings. And so if you look at this, you go, okay, delta S universe should always be 0. Now it's not the case. And so here we have liquid going to the gas. And so this is evaporation at 100 degrees Celsius at the boiling point. And so we plot the enthalpy for the liquid at 100 degrees Celsius, the gas at 100 degrees Celsius. Delta S universe is delta S system plus delta S surroundings. And so the system is delta H over T, surroundings is minus delta H over T. And so delta S universe is 0. And so at the boiling point at 100 degrees Celsius, this process is reversible. Delta S universe is equal to 0. Now, what about if we raise the temperature to 110? Now, the temperature of the surroundings is constant, right? The surroundings is everything in the universe except for the system. And so the temperature of surroundings is constant. And so if we're calculating delta S of the surroundings, it'll still be minus delta H over T because the only thing that affects the surroundings is basically heat and work. But notice that our T is no longer the boiling point. Our T is actually the 110 degrees Celsius. And so because that T is greater than TB, this term here, delta S the surroundings, is less than delta S the system. And so for this case, delta S universe is positive. And this just makes a lot of sense. At the boiling point, the process is reversible. Delta S universe is 0. Above the boiling point, we know this process should be spontaneous, meaning that delta S universe is positive. And again, the way we can calculate it out is that the temperature of the surroundings is different. It's going to be higher. And so delta S the surroundings is going to be smaller. And so that's how we get delta S universe as being greater than 0. And so it's a little confusing. We see delta H over T for the system and minus delta H over T for the surroundings, but sometimes the T's are a little bit different. Now, so that we can use delta system equals delta H over T for like a phase transition. We could not use it for a chemical reaction. And again, as we saw, for phase transitions at that temperature, so for boiling at the boiling point, delta S universe will be 0. These two terms will be equal. But if you're not at the boiling point, those two terms will not be equal because the temperatures will be different. And so we can always calculate delta surroundings as minus delta H over T because the only thing that affects the surroundings is heat and work. And typically we're going to ignore the work. Now, for chemical reactions where you have the breaking and forming of chemical bonds, remember in phase transition, you're overcoming intermolecular forces. But if we have chemical bonds, to calculate delta S the system, we have to do products minus reactants. For phase transitions, we can do delta H over T. For both, for the surroundings, delta S of the surroundings is equal to minus delta H over T. But again, please remember, for chemical reactions, for delta S the system, it has to be products minus reactants. And so a question you could see in the future would be calculate the change in entropy of 1 liter of ice at 0 degrees Celsius when it absorbs 235 joules of heat. Well, delta S system is delta H over T. And again, delta H is just Q when we assume constant pressure and expansion work. And so we have to make sure temperature is in Kelvin. So 0 degrees Celsius is equal to 273 Kelvin. And so we have Q, which is 235 joules over 273 Kelvin. And that gives us a delta S of 0.86 joules per Kelvin. And so we use this equation when there's not a change in temperature. And if there is a change in temperature, we want to calculate delta S of the system due to a transfer of heat, we have to use this equation here. Now, both of these equations were derived from delta S system equals Q over T. And again, please remember, you can only use these equations if there's no chemical reaction, if there's no breaking and forming of chemical bonds. Now the C here corresponds to the heat capacity. But again, please remember delta H is Q, assuming constant pressure and expansion work. C is the total heat capacity. And again, we can only use that equation when we have a phase transition, but not for chemical reactions. So calculate the change in entropy when 2 moles of water at 100 degrees Celsius is converted to steam at 100 degrees Celsius. So there's no change in temperature. Our enthalpy of vaporization water is given as 40.7 kilojoules per mole. And so we have delta S is equal to Q over T. Now, we're given 2 moles, and so we're going to have to multiply our enthalpy of vaporization times 2. Also, please remember, you always have to make sure your temperature is in Kelvin. So 273 plus 100 gives us 373 Kelvin. And so we have 2 times 40.7 kilojoules per mole divided by 373, and that gives us a delta S of the system of 0.109 kilojoules per mole Kelvin. Typically, entropy is given in joules per mole Kelvin. And so when we have phase transitions, we can just use the delta H over to T to calculate delta S of the system. When we have the change in temperatures here and here and here, we can use delta S system equals C, heat capacity, times the natural log of T final over T initial. And again, phase transitions are not chemical reactions. You do not have the breaking and forming of chemical bonds. And so the heat needed to melt a solid at melting point divided by the melting point is equal to the difference entropy between the solid and liquid. The heat needed to vaporize the liquid at the boiling point divided by the boiling point is equal to the difference in entropy between the liquid and the gas. Assuming that the heat capacity of an ideal gas is independent of temperature, calculate the entropy when the temperature of 2.92 moles of monatomic ideal gas is lowered from 107.35 degrees Celsius to minus 52.39. And so we're lowering the temperature, and so the entropy should get smaller. And again, we're looking at the entropy of the system. And so we can change from Celsius to Kelvin. Remember that T Kelvin is equal to T Celsius plus 273.15. And so 107.35 degrees Celsius is 380.5 Kelvin, minus 52.39 Celsius is 220.76 Kelvin. And again, if we have a change in temperature, calculating a change in entropy of the system, it's equal to heat capacity times the natural log T final over T initial. Our heat capacity is given as 20.79. That's per mole, and we have 2.92 moles. And so N symbolizes the number of moles times the heat capacity. And so we have 2.92 moles. This is the heat capacity times the natural log of 220.76 Kelvin over 380.5 Kelvin. And that gives us a change in entropy of minus 33 joules per Kelvin. And again, we saw that we're reducing the temperature, and so we should expect negative delta S, and that's exactly what we see. So for exothermic reactions, does the entropy of the surroundings increase or decrease? So we just calculated the entropy change for the system, but what about for the surroundings? Now hopefully you remember exothermic means that heat's going from the system to the surroundings, and so if the surroundings is gaining heat, its entropy should be increasing. And so delta H less than 0 corresponds to exothermic reactions. And so for all exothermic reactions, delta S of the surroundings is greater than 0. And so for endothermic reactions, delta H is positive, and that means delta S surroundings would be losing heat, and so delta S surroundings would be less than 0. And again, we can always calculate delta S of surroundings as minus delta H over T. And again, delta H is always going to be in terms of the system. Now, if we go back to the equation of delta S universe equals delta S system plus delta S surroundings, and again, we just saw that delta S surroundings is always equal to minus delta H over T. And so that gives us delta S universe is equal to delta S system minus delta H over T. Now, this is really kind of cool. Notice that we've converted from worrying about the universe to just worrying about the system. You know, the second law says if the entropy of the universe would increase, that means it's spontaneous. But how the heck do you calculate the change in entropy for the universe? Well, by defining the system as being a closed system, and hence delta S surroundings is minus delta H over T, we can actually just calculate everything in terms of the system. And so for a chemical reaction, delta S system is not going to be equal to delta H over T typically. Delta S surroundings is always equal to minus delta H over T no matter what the process is. And so delta S universe is equal to delta S system minus delta H over T. And so are all exothermic reactions spontaneous? Again, please remember exothermic means that heat is going from the system's surroundings. Well, exothermic means that delta S surroundings would be positive, but doesn't say anything about delta S system. Delta S system could be positive or negative, and so exothermic reactions are not always spontaneous. Some are going to be spontaneous, some are not going to be spontaneous. You have to know both the system and the surroundings. You could also ask, would all endothermic be non-spontaneous? And again, exothermic and endothermic just tells us delta S is surroundings. It doesn't tell us delta S system. For a reaction for delta S system, we have to do products minus reactants. So if delta H is less than 0, that's exothermic. Heat's going from the system's surroundings. And if delta S system is positive, then that tells us this is spontaneous, right? Delta H less than 0 tells us delta S of the surroundings is going to be positive. And we're told that delta S system is positive, so that tells us delta S universe must be positive, and so it would be a spontaneous process. And again, spontaneous does not mean instantaneous, but means does occur without any outside intervention. If delta H is greater than 0, that corresponds to endothermic process. Heat's going from the surroundings to the system, so delta S system would be negative. Delta S surroundings would be negative. And if delta S system is negative, that means delta S universe has to be negative. So we have to know both the delta S system and delta S surroundings to know delta S of the universe. And so delta S of the universe can be determined by delta S system and delta H of the system. And so if delta H and delta S have the same sign, whether or not delta S universe is positive or negative depends on the relative sizes. Right, so if delta S system, delta H of system both positive, whether or not delta S universe is positive or negative depends on the relative signs. If delta S system, delta H of system both negative, again, it's going to be whether or not delta S universe is positive depends on the relative signs. So here we have a reaction. And looking at the reaction, can we determine if delta S of the system is positive? So if we look at the number of gas particles, typically the number of gas particles can help us determine delta S of the system. Remember, more gas particles means delta S system is positive. And so we have 18 gas particles reactants. We have 13 products. And so our reactants have a higher entropy. And so delta system would be negative. Remember, delta system is products minus reactants. Now, is delta surroundings positive or negative? Well, if we look at this reaction, if it was written backwards, it would be combustion reaction. And so that means heat would be a reactant. And so that means that's got to be endothermic. And so heat is going from the surroundings to the system. So delta surroundings is going to be negative. Now, the universe is just equal to the system plus the surroundings. So in this case, delta S of the universe would be less than 0. And so that means that this process would be non-spontaneous. Means that it would not occur without any outside intervention. If we look at another one, here we have a liquid going to the gas. And so we have one gas particle as a product, none as a reactant. And so delta S of the system would be positive. Now, if we want to go from liquid to gas, we always have to add heat. And so that tells us delta S of the surroundings is negative. Because again, heat's going from the surroundings to the system. Now, if we look at it, this universe is the system plus the surroundings. One is positive, one is negative. So we can't tell the sign of delta S universe. And so that means that this process, whether it's spontaneous or non-spontaneous, depends on temperature. Now, if we look at it, obviously above 100 degrees Celsius, this is going to be spontaneous. Below 100 degrees Celsius, this is non-spontaneous. And so it actually has a transition temperature. If we look at this one, and so we have one gas particle reactant, two gas particles products. And so that tells us that products have higher entropy, so delta system is positive. Now, if we want to break that bond, right, because what's happening in this reaction is you're going from a fluorine molecule to two fluorine atoms, so you're breaking a bond. So you'd have to add heat. So again, that would be an endothermic process. Heat's going from the surroundings to the system. And so delta surroundings is going to be less than 0. And so the system is the universe is the system plus the surroundings. The system's positive, surroundings negative. And so we can't tell delta S of the universe. And so whether or not that reaction is spontaneous depends on temperature. So if delta S of the system is positive, the entropy of the system increases. And if delta H is negative, meaning exothermic, that means the entropy of the surroundings increase. Both the system surroundings entropy increases, and so that means the process has to be spontaneous, because delta S universe would be positive. If delta S of the system is negative and delta H is positive, meaning endothermic, meaning the delta S of surroundings decreases, then both the entropy of the system, entropy of surroundings decreases, and so delta S of the universe would have to decrease, and that would be a non-spontaneous process. If both delta S of the system is positive, delta H is positive, if the system's positive, if delta H is positive, that means you have endothermic process, so the entropy of the surroundings would decrease. And so one is positive, one is negative. And so you have to look at, it's going to depend on temperature, whether or not spontaneous or non-spontaneous. And so we saw that the statistical definition for entropy is the best way of thinking about entropy. K natural log W, it's all about the number of configurations. We saw that entropy can be changed by adding heat. So delta system equals Q over T if you have no chemical reaction. We also saw delta S of the surroundings equals minus delta H over T. And often this is the best way of calculating the change in entropy. And so the second law says if the entropy universe would increase, then it's a spontaneous process. Now, it seems really hard to calculate change in entropy universe, but it's kind of cool. By defining the system as being closed system, we see that we can calculate the delta S of the system by products minus reactants. We can calculate delta S of surroundings as minus delta H over T. And so we can actually calculate delta S of the universe from delta S system and delta H of the system. I hope that was helpful.